All right, hello everyone, and welcome to another Astrocheminar put on by us, the ACS Astrochemistry Subdivision, with support from the ACS Physical Chemistry Division. You can see that the Physical Chemistry Division ACS account is here on the panel for us. They sponsor this webinar account and allow us to put on these seminars for you. So my name is Kyle Crabtree. I'm from UC Davis, and I'm the chair of the subdivision this year. And I'm joined today by our other officers, our past chair, Heather Abbott-Lyon from Kennesaw State University. And behind the Physical Chemistry Division ACS account is Chris Bennett from University of Central Florida. Not able to join us today, but part of the officer rotation is our vice chair, Michelle Nuevo from NASA Ames and the Bay Area Environmental Research Institute. And we have our subdivision secretary, Dave Woon from the University of Illinois. Serving as an officer is a great way to contribute to the astrochemistry community. And so if you or someone you know may be interested in serving as an officer in the future, please do get in touch with us. We'd be happy to discuss with you further. I wanted to take a moment, since this is the first seminar that we've had since the summer break. I wanted to let you know of a few recent highlights, some activities that have gone on recently, and some things that are going to be upcoming. So at the ACS Fall 22 meeting, we had a great symposium on inorganic and organometallic astrochemistry that was organized by Leah Dodson and one of today's speakers, Nate DeYonker. We also recently co-produced an ACS webinar that was given by Professor Brett McGuire from MIT on how we study molecules in space, finding and analyzing cosmic carbon. And so that webinar was recorded. You can watch the recording on the website, and it looks like Chris has just posted a link to that in the chat. So you can check that recording out to hear about some recent astronomical detections of large carbon-bearing molecules in space. Coming up in a couple of weeks, Brett also runs an online astrochemistry symposium series called the Astrochemistry Discussions. Their next symposium will be in 2 weeks on September 28th at 10 a.m. Eastern. And the speaker at the next event is actually going to be me. So if you want to hear me talk about some of my research and career, you can feel free to check that out. We just posted a link to the website where you can register if you're interested. Next year, at the fall ACS National Meeting, we are going to be putting on a symposium titled The Astrochemistry Subdivision, A Decade of Progress and Prospects for the Next Decade, kind of in commemoration of our 10th anniversary of the founding of the subdivision. And this is organized by our subdivision secretary, Dave Woon, and Olivia Harper-Wilkins. We're also interested in developing proposals for symposia to be hosted during the 2024 year at an ACS national meeting. So if you might be interested in organizing a symposium, please do get in touch with us for details. You can get in touch with us by checking out our website. There's a link to the website in the chat as well. So with that, I want to move on and introduce our first speaker for today. So our first speaker is Dr. Jessalyn DeVine. Jessalyn did her PhD at UC Berkeley with Dan Newmark, where she worked on gas phase anion photoelectron spectroscopy, and she is currently a Humboldt postdoctoral fellow in the Department of Dynamics and Surfaces at the Max Planck Institute for Multidisciplinary Sciences in Göttingen, Germany. She currently works with Alex Bogke on processes that happen on surfaces, and we're going to hear a little bit more about that today. So if you have questions during the talk, please do post those in preferably the Q&A tab. You can also use the chat, and we'll be happy to address those after the talk. So Jessalyn, please go ahead.
Okay, thanks, Kyle, for the introduction. Yeah, so it is 8 p.m. here in Göttingen, so I'm a little sleepy. But so usually my group looks at surfaces, but the stuff I'll be talking to you about today is actually about what happens in a CO ice when you excite it with an infrared laser. And so, oh, is it not working? Okay, there we go. Okay, so just to put this in an astrochemical context, as I'm sure all of us astrochemists are familiar with, there's been lots of these complex carbon-rich molecules identified in astronomical measurements. And then the question that astrochemists need to answer is, how do these molecules form? And in particular, how do these carbon atoms find each other and link up? And so carbon monoxide is the most abundant carbon-containing molecule in the universe, and it's especially common in interstellar ices, where it's usually bombarded with high energy radiation. And so it's typically believed that the chemistry that leads to more complex species like these starts off in solid CO, so CO ices. And so because of this, a lot of other groups do these studies where they basically try to mimic the conditions in the interstellar medium. So they make a CO ice and then they bombard it with high energy radiation like UV or X-ray photons or charged particle beams. And then they look at the products that form using usually infrared spectroscopy. So for example, in this paper from Rolf Kaiser's group, they hit their sample with a 5,000 EV electron beam and saw formation of all these different carbon chains and carbon oxides. And by analyzing the relative signals of all of these things, they were able to figure out a really complex mechanism and break it down into elementary reaction steps. And this is really the power of these high energy experiments, which is that you can answer the question of what bonds are being broken and formed in order to form the molecules that we see in space. However, if you hit a molecule with 5,000 electron volts, you will put it in a reactive state, but it's not necessarily clear what that state is. And so it's harder from these experiments to get a state-specific picture of what's happening. So not just what bonds are being broken and formed, but what are the states that the molecules need to be in order for these things to happen. So in our group, we do things a little bit differently. We look at what happens in these ices when we put in much smaller amounts of energy. So it all started off with these laser-induced fluorescence experiments, where you take a CO ice and you hit it with an infrared laser, and that excites some of your CO molecules into the V=1 state. And then since it's a laser-induced fluorescence experiment, you look for the photons that are emitted as the system relaxes. And then for each vibrational state that you have populated in your sample, you'll get a different frequency photon. Now, naively, you might think that that would be a pretty boring experiment because you're going to such a low energy state that it can really only have one decay pathway, V=1 to V=0, giving you a single emission line. But experimentally, they see many emission lines, meaning that they're seeing emission from many vibrational levels of CO, and they're able to assign these as coming from CO with up to about 37 quanta of excitation, which corresponds to over 7 eV of internal energy. And interestingly, this energy threshold where they see population and up to V=37 is right around the energy of the first electronically excited state of CO. And so it's been proposed that just through exciting with an infrared laser, you can actually get population in this triplet state, but that isn't something that's been confirmed. Okay, so how is this all happening? How are we putting in less than half of an EV of energy and getting into such high states? So this happens through vibrational energy pooling, which I'll illustrate using this 2D grid representation of a CO crystal. So each box here is a CO molecule, and then the number in the box is just the number of the quanta of vibrational excitation that it has. So when we hit our sample with our laser, we get about 50% of our molecules in the V=1 state. And then what can happen is two molecules that are excited can undergo this non-resonant pooling process and when I say non-resonant here, what I mean is that we're changing the vibrational state populations in our samples. So now we have a molecule in V=2. And this can continue, and it turns out that the rate of this actually gets faster as you increase V. So basically, as this molecule gets higher and higher in this vibrational ladder, it becomes more and more likely to further accept more quanta. So this is the main mechanism where we start to get these higher states. And now the way that I've drawn this, you might think this will really only get you so far, is you basically empty out all of the energy surrounding the central molecule. But there's also this resonant pooling process. And so here we haven't changed the overall vibrational state populations, but these quanta of excitation have moved between molecules. And this is much faster than the non-resonant pooling. And so the vibrational excitation is highly mobile on the surface, allowing you to get even further up the vibrational ladder. Okay, so you can take all of this pooling framework and code it up in kinetic Monte Carlo simulations and then figure out what vibrational states you populate and then simulate a fluorescence spectrum. And so if you do that and you only include these nearest neighbor interactions, like the ones that I've shown here, you get this red spectrum down at the bottom, and you can see you don't get nearly as many emission lines as you see experimentally, meaning you're not populating as many vibrational states. So in order to reproduce experiment in these kinetic Monte Carlo simulations, they needed to include pooling between molecules that were much further apart in the crystal. And so what that ends up meaning is at the highest energy states, so the CO molecules that really get to the upper end of this vibrational ladder are very dilute in the crystal because all of the energy over a fairly large region of the sample has gotten dumped into a single center. Okay, so through all of this, we have a pretty good protocol for using an infrared laser to get this dilute concentration of CO molecules with a considerable amount of energy in them. And so then we wanted to see if this can lead to actual chemistry. So to do this, we set up an experiment that's very much in the spirit of those high energy experiments, where the idea is to make a CO crystal in a vacuum chamber, irradiate it, and then monitor the chemical composition using infrared spectroscopy. But here, our radiation source is going to be our infrared laser. So here I'm showing the spectrum of the initial sample. So it's dominated by the CO lines because it's a CO crystal. And then we'll be looking in this low intensity view to look for trace amounts of new molecules forming. And to start off with, we have a bit of a CO2 impurity that's kind of hard to get rid of, but otherwise our samples are very pure. Okay, so then the idea is to excite with a fixed number of laser pulses and then measure an FTIR spectrum, and then excite, measure, et cetera, repeat until the spectrum stops changing that much. And so then, now that we have this final spectrum, we can look at it and figure out what's changed. So first of all, the intensity of these CO features has gone down a lot, so we've lost CO from our sample. But more interestingly, this CO2 band seems to have changed. And if you look at the area under this band over the course of the experiment, it goes up by quite a bit. Now we do have in our vacuum chamber some residual pressure of CO2 that's pretty hard to get rid of. And so this could just be from background absorption. So we repeated this experiment with the laser closed, and then we get a roughly linear increase just from CO2 absorbing into the sample over time. But more importantly, we don't see nearly as much being formed as we do with the laser on. So something is happening with our laser hitting the sample that is leading to CO2 forming. And then the only other evidence of change that we really see in these spectra is this new band that pops in at 2250 wave numbers. And this belongs to carbon suboxide. So we're making carbon-carbon bonds in our sample with our infrared laser. So other than these things that I pointed out here, the spectra are pretty boring. So now we can move forward and quantify this chemical change. So we use Beer's law and then get out these column densities. So it's like a 2D concentration. And I'll just point out that, so this is for 3 different crystals of different thicknesses. And I'll just point out that the CO2 data has been corrected for the initial impurity, as well as that roughly linear increase we saw from absorption. And with that correction, you can see that we make pretty much the same amount of both product molecules. And then doing some simple Gen Chem stoichiometry homework problem, you get, I guess, for the overall reaction. So 4 CO molecules going to 1 of each product. But now if you look at the numbers, so the units of this are 10 to the 14 molecules per centimeter squared. So on this scale, we're making about 0.15 of both product molecules, which given this stoichiometry, we should be losing, that math is not right, we should be losing on the order of 1 on this scale, but we're losing like 300. And also, particularly for this thickest sample, we noticed that whenever we hit our sample with the laser, we saw spikes in the UHP pressure. And so it seems like the majority of our CO is being lost by desorption. So CO is going to the gas phase instead of converting into products. And then the last kind of observation we can get from this is the saturation behavior, which just refers to the fact that these curves kind of level off as we've exposed the sample to more and more laser shots. So these are the 3 key things that we really want to be able to explain to get an understanding of the chemistry that's happening in our sample. And so in order to do that, we need a mechanism. And fortunately, both of these molecules were observed in that electron bombardment paper. And so we have a pretty good starting point. So in that work, everything gets kicked off when you have a highly excited CO molecule react with another CO, forming CO2 and leaving behind a carbon atom. And then this carbon atom can react with another CO to form C2O. We don't see any evidence for C2O in our spectra, but this molecule is known to be pretty reactive and will readily react with CO to form carbon suboxide. And we don't see any evidence for any other molecules forming, so we think that these are really the 3 elementary reaction steps that we need to consider, which fortunately gives us the same overall stoichiometry that we kind of guessed from our data. But there's still this question of what is this excited CO molecule? In electron bombardment paper, it could have been anything. In particular, these 3 reactions are known to occur when CO is in that triplet excited state. And if you remember, the energy thresholds that we see in vibrational energy pooling are right around the energy of that state. And so maybe, we're forming a triplet and that's what's leading to products. But then you're saying that carbon monoxide, a small molecule with no metal atoms in it, is undergoing a spin forbidden transition. And so that seemed a little fishy to us. And so we started wondering, can we actually access the triplet state through pooling, and is this necessary to form products? So I did a lot of electronic structure calculations to try and answer these questions, and I don't really have the time to go into the details here, but what came out is an overall mechanism that actually explains all of our key observations. And so I'll kind of walk you through it, and I'll fill out this potential energy diagram as we go from 4 CO molecules to CO2 plus C3O2. So here the black lines are going to be showing the singlet energies, and the red will be showing the triplet. Okay, so to start off with, we excite our sample, we induce cooling, and then we get this dilute concentration of CO molecules in high vibrational states. And then what can happen is a CO molecule that's really at the upper end of this vibrational ladder can meet up with another CO to form a metastable CO dimer. Now in the singlet state, there's no way for this dimer to dissociate and form CO2. Instead, what this dimer prefers to do in the singlet state is kind of rearrange and then ultimately dissociate. And that dissociation is exothermic, and so it releases heat, which then drives the desorption of CO. And since the majority of these dimers are going to stay in the singlet state, this is why our CO loss is dominated by desorption. But as I just kind of hinted, there's something else that can happen. So if you look at the energy ordering of the singlet and triplet here, it's swapped. So with 4 CO, the singlet is lowest energy. Here, the triplet is lower in energy. And so we've gone through a curve crossing. And when you go through a curve crossing, electronic transitions become much more likely. And indeed, if you calculate the intersystem crossing rate for this dimer structure, you get a 10 to the 15 times acceleration when you do the same calculation for just a CO molecule. And so, I mean, this CO dimer is still metastable, so it's still not super likely, but there is a small chance that this dimer will undergo a spin forbidden transition, landing you with a CO dimer in the triplet state, and then that dimer can dissociate to form CO2 plus a carbon atom. And so now that we have a carbon atom, that will react to form C2O, and that turns out to be barrierless. And then that will react to form C3O2, which also turns out to be barrierless. And since both of these are barrierless, this is why we see equal amounts of both products forming. Basically, once you get to CO2, you just keep rolling downhill until you get to carbon suboxide. And then you see here again, we've swapped the energy ordering of the singlet and triplet. So we've gone through another curve crossing. So there's probably another ISC transition happening here. Okay, so now the last thing we need to explain is the saturation behavior. And in order to understand that, we need to think about what happens as we repeat this cycle of exciting and reacting and building up a concentration of these polyatomic product molecules. So I'm showing 2 of these grid representations of our CO ices. So here we have a pure CO ice, so this is early on in the experiment. And then here is later on where we've got some polyatomics that I'm indicating with these black boxes. And so what can happen when you have these polyatomics is that the energy that's usually bouncing around in the pooling can land in one of these polyatomic molecules. And then what happens is that it rapidly undergoes IVR. So the energy rapidly gets distributed along all of their normal modes, and then ultimately gets lost to the photon bath of the surroundings. And so basically they act as energy sinks. And so as you build up more and more of these polyatomic molecules, it limits the highest vibrational state you can access through pooling. And in order to unlock the chemical changes that we see, we need to get to this metastable dimer structure. And so as you build up these product molecules, you're less and less able to form that dimer. Okay, so I'll just wrap up. So the main conclusion that we got here, I guess, is that you don't need extreme conditions to form carbon-carbon bonds in CO ices. And we've really kind of mapped out the lowest energy pathway that can lead to these molecules that have been observed in space. And also, maybe this is more interesting for us than for astrochemists, but we've kind of got a more subtle view of why those energy thresholds are there in those cooling experiments. So remember, previously it was suggested that once you get into these high vibrational states, CO molecules can undergo intersystem crossing, and so that's why you stop seeing them. But really what happens is that it can form a dimer, and then that dimer can go in the triplet state, but most of the time it doesn't. Okay, so I'll just do some acknowledgements. So thanks to my advisor, Alec Botke, who's the department director. And then this is the group that I worked with. So group leader, Dirk Schwartzer, and then the 2 grad students, Arnav is still with us, and Yasha is now working in Berkeley with Dan Newmark. And then thanks to the Botke group, and thank you for your attention.
All right, thank you, Jessalyn. That was a really fascinating talk. A reminder for everyone, if you have questions, please do go ahead and open up the question and answer session tab or the chat, and you can start posting your questions there. We do have one question already from an anonymous attendee, and they ask whether there's any possibility of the oxides of these carbon molecules to behave like magnetic domains.
Okay, yeah, that's not something that I've thought about. I have not considered the magnetic properties of any of these molecules whatsoever. It would be interesting to look into, but really yeah, I guess that would be more relevant to the high energy experiments also, because so the saturation behavior that we see, that happens when these products are about 0.01% of the total sample. And so they're not forming a domain, they're scattered throughout.
All right, another question just came in saying that a real CO ice is probably dirty. And so how dilute can the CO molecules be for this kind of chemistry to persist?
Yeah, it has to be pretty pure. So I don't think that this chemistry is what actually happens in space. It's more that because it happens in the lab, we can figure out kind of the minimum energy conditions that you need in order to form these things. And you learn about the electronic states that need to happen. So it's not, our experiment isn't so much about reproducing interstellar ices. It's about, we were just trying to see pooling really, and then we saw this extra stuff happening. But it is still astronomically relevant because it's telling you about the states that need, the minimum energy states that need to be there in order for these transformations to happen.
Okay. I have perhaps before I ask any question of my own, there's another question that just came in from another anonymous attendee asking whether Arrhenius factors are used to determine the activation energies of these processes.
So all of the energies that I'm showing are literally just they're the optimized geometry, single point energy. I did DFT basically, and that's 0 point energy corrected. I didn't do any Arrhenius factors or thermodynamic stuff here.
Okay. Well, my question is somewhat naive. This is the first time I've seen this a concept of vibrational pooling. I imagine this is something that just exposes my ignorance in the area. But when I teach, undergraduate physical chemistry, and we talk about statistical thermodynamics and entropy concepts, we always discuss the weight of a particular configuration is maximized when you kind of distribute energy among a wide variety of states. And it would my naive reaction is just that how is this consistent with entropy and statistical thermodynamics for this vibrational pooling effect to occur?
Yeah, this is a question I've gotten before, and I maybe unfortunately don't have a super satisfying answer other than just saying, the rates get faster as you increase that vibrational quantum number. It's just a way that through dipolar interactions. And the numbers just kind of work out that way. And also, we observe it. So the modeling that they have seems to agree with the experiment. As for relating it to entropy, yeah, that's a good point, but I haven't really thought of a good way to answer that question yet.
Sure. Oh, another question just came through. I'm having trouble scrolling. Okay, so a question from Marissa Weichman. Have you thought about follow-up experiments where you dope the CO ice to look for reactions between, I think, excited CO and other simple molecules? Any most exciting targets? Yeah,
that would be a future direction to go in. Right now, what we're working on, well, a bunch of stuff, bro. But right now, what we're actually going to work on is looking for UV emission from these things, which would confirm whether or not we're actually populating the triplet state. But yeah, there's a lot you could do with, and gradually decreasing basically the concentration to answer the question of how pure does the CO ice need to be. Yeah, there's a lot you could do there, but we currently aren't planning because our group isn't an astrochemistry group. Maybe in the future I can look into this if I ever have my own experiment.
Oh, all right. Well, I think with that, it is time for us to move on to our next speaker. But thank you again, Jessalyn. That was a great talk. I really enjoyed it. Our next speaker today is Professor Nate DeYonker. Nate did his PhD at the University of Georgia with Henry Fritz Schaefer, and then worked at University of North Texas with Angela Wilson and Thomas Kundari. He then moved on to the University of Memphis, where he was initially a research scientist, and then was hired in on the tenure track as a faculty member, where he currently is an associate professor. His research focuses on applying quantum chemistry to the spectroscopy of small astronomical molecules, and he has another effort in computational modeling of enzymes at the atomic level, developing models, effective computational techniques for that, for which he's been awarded an NSF Career Award. And so today he's going to talk to us about big trouble with little molecules. So please, Nate, take it away.
All right, thanks, Kyle. Thanks, Jessalyn. All right, hey, everybody. It is great to be here. Yeah, so currently, most of my group's funding is to look at atomic level models of enzymes. And when you know, I'm not a formally trained biologist or biochemist by any means. I learned this all kind of on the job, and looking at proteins and looking at the metal carbon bonds of enzymes and proteins and their complexity is just spectacular and always overwhelming. But then when we think about the complexity of known metal carbon bonds in the gas phase in space, our molecular complexity is a little bit lacking. Right, we've got these metal cyanides and these metal polyines. You know, they're all linear molecules with pretty strong permanent dipole moments. But certainly, we're not talking about things with hundreds or thousands of atoms, and that's kind of a tongue-in-cheek argument, right? I mean, of course, there aren't complex proteins floating around in the interstellar medium or hitching a ride with comets, but you know, but I still like to ask the question: when does astrochemistry become astrobiology? When you know, we don't know at all, because there's this gigantic knowledge gap in the spatial regime between what is known in the gas phase and even really surface chemistry of space compared to the complexity of life and even origin of life on Earth. And yeah, so very tongue-in-cheek argument. Proposal reviewers especially hate when I make the comparison between proteins and ISM triatomics. So I've stopped doing that. But the highly accurate spectroscopic data or obtaining you know, reference data and reliable data for small open shell inorganic molecules is, since the very beginning of my career, has been a huge challenge for theory, for observational astronomy, and for spectroscopy. And this literally does go back to my first week of grad school, where Fritz Schaefer asked me if I was interested in an astrochemistry related project, which I said, heck yes. And he showed me this paper by Paul Dagdigian, famous spectroscopist from Johns Hopkins University. And while most of the metal monocyanides that had been characterized spectroscopically had had a cyanide bonding, Paul observed the iron isocyanide, which is quite interesting. And he made the assumption in this paper that iron monoisocyanide would be more like the high-spin sextet iron monochloride and iron monofluoride molecules that had been studied versus the sort of low-spin quartet state iron monohydride. And so it took a very long time to get this first project finished. And what I found in my first author paper was that there was intense competition between the quartet and sextet spin states in both of these isomers, and that perhaps the iron cyanide isomer might have a lower energy and be more stable than the isocyanide. And while the isocyanide should have a sextet ground state, our calculations suggested that the cyanide might have a quartet state. So what's very interesting is that there is a fairly low barrier of isomerization So then on the pathway to isomerizing from the cyanide to the isocyanide, that there would also have to be some kind of spin flip. And so fairly famous spectroscopists tried to isolate and characterize both the cyanide and the isocyanide. Michael Heaven, Lucy Zuras worked on this for, groups worked on this for 8, 9, 10 years until finally in 2011, Lucy identified the cyanide in the quartet delta ground state, both terrestrially in her lab and in by observation of IRC plus 10216. And still, as recently as 2018, some computational chemists in the literature disbelieve the results that Lucy and I published independently, calling Lucy's pure rotational experiments erroneous. So, you know, still waiting for somebody to prove us wrong and come out with a better methodology and better experiments. But the kind of controversial part of these first papers on iron cyanide was that we use multi-reference methods in computational chemistry to study problems that have what's called strong or non-dynamical correlations. So this is sort of the kind of long-range electron correlation effects from near degenerate configurations, versus the dynamical correlation that is short-range electron interactions. And what I've found over the years is that sometimes these multi-reference methods like CASP-PT2 and the multi-reference configuration interaction with singles and doubles, they account for the non-dynamical correlation, but they're not powerful enough to capture all of the dynamical correlation. Whereas coupled cluster theory is inherently single reference and doesn't capture this non-dynamical correlation at all. But if you push it beyond conventional techniques, because coupled cluster and configuration interaction will eventually converge to the exact solution of the correlation problem, does single reference theory eventually start to soak up some of this multi-reference character? And so as an independent researcher, I've taken kind of a holistic approach where my group combines multi-reference theories and single reference coupled cluster theories when needed. And really, right, in my group, we don't really worry too much about reactivity. We don't, until recently, we didn't worry about rotational and vibrational properties because we were so concerned with reliably obtaining the right electronic structure and the right electronic ground state configuration. Because if you don't have the right spin multiplicity for the molecule, or you don't have the right, the right arrangement of the electrons in the molecule, you're going to lead experimentalists down expensive and time-consuming paths towards the wrong answer. But now, finally in the last 5 years, thanks to collaborators like Brian Fortenberry at Ole Miss, we've become confident enough pinning down the electronic structure of these molecules that now we can think about row vibrational spectroscopy. And so Ryan and I and my amazing research scientist, Chinyi Cheng, published this first paper, kind of tiptoeing into the shallow end of the pool, looking at closed shell copper containing molecules. And so we use this quartic force field technique that kind of pioneered by Tim Lee, in the sense that it uses black box single reference coupled cluster theory, and there's really nice scripts and integrated code that gets you from getting your vibrational force field and moving that all the way to getting good row vibrational properties and even row vibrational Hamiltonians. And so Ryan and I had to change some of the kind of black box techniques in order to be more appropriate for inorganic species, using scalar relativistic corrections throughout, using a complete basis set extrapolation scheme more appropriate for transition metals, and then looking at sort of post gold standard, starting to try to get to platinum standards for coupled cluster theory in terms of accuracy versus cost. It's very expensive stuff. So thinking about using additive corrections for small basis set CCSDT parentheses Q, and looking at the effects of inner core correlation. So the results that we got in this first paper, this first inorganic QFF paper, were phenomenal. Looking at the copper monohydroxide, getting vibrationally average properties really close to microwave experiment, getting vibrational frequencies within 1 to 2 wave numbers of experiment. That's the kind of accuracy we're expecting when we look at organic molecules, small organic molecules that don't have this electron correlation problem. So Ryan and I, back to being kind of silly and trying to market inorganic astrochemistry a bit, published this Accounts of Chemical Research review of the work that we had done together so far on inorganic astrochemistry. And then some of the work some of the other work over the past 5 years is to look at gas phase metal carbon bonds and their relevance in the interstellar medium. So especially with one of my first undergraduates, Shelby Dickerson, who got her PhD in organic chemistry at University of South Carolina. She did fantastic work looking at the 3D metal monoacetylides, so the metal C2H molecules from scandium through zinc. And we got some really great reference data for that. Found some more bad actors that have intense multi-reference character. And then, now that we're confident with electronic spectroscopy, I've started to directly work with Lucy Zuras. Lucy Zuras and her group. She published a paper 8 years ago, building off of work by the Redondo and Largo group about a decade before that, looking at the scandium dicarbide, and we wanted to revisit that and look at the isotopologues. So there's no intense multi-reference character in this molecule, so it's a good place to start. It's a good place to move on from those copper triatomics and tetraatomics. It's open shell, it's got a transition metal, but not so much multi-reference character. And again, we got incredibly good comparison with experiment. We plugged our kind of purely computational Hamiltonian into pGopher, and we got rotational levels that were between 90 and 200 megahertz from the observed lines in Lucy's experiments. So for somebody as a postdoc that was obsessed with thermochemistry and computing enthalpies of formation within 1 kcal per mole of the experimental value, errors of 100 megahertz, which is something like 8 times 10 to the negative 5 kcal per mole. That's an accuracy, a level of accuracy that I would have never dreamed of as a grad student and a postdoc. So that's really exciting, because are we to the point where computations can reliably predict pure rotational spectra? One interesting thing that came out of this, it's well known that treatment of electron correlation passed what the so-called gold standard, which is large basis set CCSD parentheses T. That moving beyond that is really important for getting accurate vibrational spectra, especially when you're dealing with transition metals. So it's well known that CCSD-T and CCSD-T parentheses Q can have offsetting effects that can shift fundamental harmonic and fundamental frequencies around quite a bit. But what's kind of interesting is that we see that an often neglected contribution to spectroscopic properties can be the inner core electrons, the 1s, 2s, and 2p electrons of scandium. And we find here, very interestingly, that that for the C2 stretch, that inner core scandium correlation doesn't have any effect, but it can shift the scandium carbon symmetric stretch and the bending mode by up to 2.5 wave numbers. And there's a non-negligible shift to principal rotational constants. So this is a good trial run that we predicted, nearly predictive pure rotational spectroscopic constants, and really great agreement with the isotopologues that were published that were studied by Lucy. So now let's think about some more challenging molecules. So in the interstellar medium, trying to increase the inventory of gas phase molecules in space. There's been a recent focus on magnesium due to its high interstellar abundance, and potentially because there's a little snowball effect of, okay, these molecules are stable, they have large dipole moments, so let's see how many more we can find. And there's an obvious connection with magnesium carbon, magnesium oxygen bonds, obvious relevance to exoplanet formation, geochemistry, material science. And one thing that Ryan and I became interested in is, okay, you've got very important interstellar molecules like C3 and N2 that have no dipole moment. So can we stick a metal onto these rotationally invisible molecules and study the properties of those molecules that may act as tracers for these important small molecule fragments? And so the Kundashara group has been responsible for identifying a lot of these magnesium containing molecules in the interstellar medium in IRC plus 10216. These references are old. They've published 2 or 3 more excellent papers in the last 3 or 4 years. So we wanted to focus on magnesium tricarbide, and the Redondo and Largo team had published some theoretical work on this about 20 years ago, looking at MgC3 and various levels of theory, looking at harmonic vibrational frequencies. And what they found, surprisingly, is that there's spin competition between the singlet and triplet states of this molecule. So they were able to rule out some of the isomers as being very high in energy, but they found that there was isomeric competition and spin state competition, kind of unusual for a magnesium containing molecule. So what is the ground state isomer? Is it this kind of diamond structure, or what they call this kite structure? Or no, this is the fan structure versus the kite structure versus the zigzag structure. And then is the singlet or triplet state lower in energy? So as the rigor of their computational methods increased, it kind of came down to 2 candidates, either the singlet or the triplet diamond state. And what they found with perturbation theory, MP2 theory, is that the triplet state was lower in energy. But when they did these composite approaches, the Gaussian 1, Gaussian 2 methods that include core correlation and some more basic basis set effects and some empirical corrections, they found that the singlet was favored. Now, when they ran valence coupled cluster calculations, they found that the singlet was favored, but then as their basis sets got larger and larger, then that tipped the scales in favor of the triplet. So they weren't able to conclusively label the singlet or triplet diamond as the ground state. All right, so we clobbered this with correlation consistent basis sets and core valence correlation and relativistic effects, and we found a couple interesting things that agree with the previous results. First is that as we increase the size of the basis set, improve the treatment of the 1 electron situation, that indeed the triplet diamond became the lower energy isomer. But then as well, the inclusion of core valence correlation also kind of favored the triplet. So okay, so things are leaning to the singlet and triplet being isoenergetic. We're talking about 0.2, 0.3 kcal per mole here. But where? Right, so how do we kind of pin this down? And we need to go beyond CCSD parentheses T. And when we do that, I have to move my face out of the way so I can get my laser my virtual laser pointer in the right place. So when we add all of the bells and whistles, this composite method dubbed CCC and CCCR, the acronyms that I blame Ryan for these acronyms, we see that the triplet diamond is lower in energy by about 0.3, 0.4 kcal per mole. But then when we add post CCSD parentheses T corrections, CCSDT actually with larger basis sets then also favors the triplet diamond. But then when we move to parentheses Q, there's this shift by 3 kcal per mole in favor of the singlet diamond. So that's kind of a gigantic change. And we find that our additive corrections, so our composite method plus the parentheses Q additive corrections favors the triplet state by more than 2 kcal per mole, and that's in agreement with the multi-reference methodologies, this MRCI. Right, so when we're trying to study the multi-reference character of molecules, there are these couple cluster amplitude diagnostics that Tim Lee and Daniel Crawford came up with 20 years ago that are useful to figure out if something has multi-reference character or not, but they're really dangerous. They're really not supposed to be the only metric used to assess multi-reference character. So if we look at these couple cluster diagnostics for the singlet state on the singlet diamond on the left and the triplet diamond on the right, we see that they're pretty much identical, and the T1 diagnostic needs to be above a value of 0.05 in order for someone to be worried about multi-reference character. So these diagnostics tell us that, okay, this molecule is not very multi-reference in either the singlet or the triplet state. But when you actually look at the value of the amplitudes themselves that aren't kind of averaged or smeared out over all of the amplitudes, we see that there's a T2 amplitude of 0.3, which is a gigantic value corresponding to a double excitation that is sort of co-dominant in the electronic wave function. So if we look at our multi-reference diagnostics, we see indeed that the singlet state is extremely multi-reference. There's a second electronic configuration that comprises about 26% of the wave function, whereas the triplet state, that leading electronic coefficient is 83% of the wave function. So that, by all indications, the triplet is single reference, but the singlet state is extremely multi-reference. So that is a huge problem. And that problem manifested itself when we tried to do our quartic force fields, and kind of all hell broke loose when we got really weird results for the singlet state. And we kept getting massively positive anharmonic corrections for our omega-3, which is our symmetric MGCC bend, so kind of doing this. So we weren't able to get reliable quartic force fields using coupled cluster theory. We could get decent harmonic frequencies using MRCI, and we did kind of we used the one type of CCSD parentheses T QFF that worked to kind of tack on an anharmonic correction to the MRCI values. And we find something really interesting, that this symmetric bend has a fundamental frequency of about 524 wave numbers, and that is not that energy is kind of far away from any of the other calculated frequencies for any of the other isomers. So if it's the singlet diamond ground state, we should see that peak at 524 kind of sticking out. In case there's many isomers in equilibrium, if we tried to make MgC3 in the lab, and then this frequency does have a large IR intensity as well, so that's good. And then of course, based on the row vibrational spectroscopy, we should be able to look at line splittings and quickly figure out whether or not we have a singlet or a triplet state as well. So we tried for almost a year and a half, we tried to figure out what is going on with the quartic force fields with coupled cluster theory, because we didn't realize just how strangely multi-reference this diamond singlet state was. And finally, I was at an ACS meeting and I asked John Stanton, brilliant theoretical chemist, if he might be able to help us figure out what is going wrong with these quartic force field calculations. And and what we figured out with John was that there is an excited, the first electronic excited state is extremely close to the bending mode of to this magnesium carbon-carbon bending mode. So when the magnesium carbon-carbon symmetric bend compresses inwards, that gets the ground state electronic wave function extremely close to the first excited state. So then there's this multi-reference avoided crossing. So we get all this wild orbital instability just by compressing the middle CC bond by 0.15 angstroms. We get complete divergence of the coupled cluster amplitudes. And when we do this same compression of that vibrational coordinate with multi-reference theory, there is no avoided crossing, but we see that the excitation energy is small enough that there's electronic coupling between the ground state and the first excited state. So we published some of the geometric properties of the skinny diamond isomer, the singlet skinny diamond as well. So overall, we looked at magnesium tricarbide and we did our best to publish rho vibrational properties beyond harmonic frequencies and principal rotational constants. We're pretty certain that once we move beyond CCSD parentheses T, that we have the singlet diamond isomer as the ground state. And so John Stanton has seen a lot of interesting toy electron correlation problems before, but when John Stanton tells you that your case study is something that he's never seen before, then that's pretty unusual. But right, we've seen problems like ozone when we break bonds, and N2 as we break bonds, and kind of non-dynamical or strong correlation takes over and screws up the coupled cluster calculations. But John had never seen coupled cluster fail so close to equilibrium for a molecule before, especially a molecule that doesn't have a transition metal in it. But we were able to get good harmonic frequencies and good quartic force field derived constants for some of the low-lying, some of the lower energy isomers, and yeah, definitely an improvement on previous data that we hope will help folks isolate terrestrially characterize MgC3. So overall, with this work, we've looked at some troublesome molecules. We've extended the black box QFF methodology to handle metal-containing molecules, and the outlook is good. Sometimes the agreement is spectacular within 1 or 2 wave numbers, but there are some situations where we see differences with experiment by about 50 wave numbers. I didn't go into this, but Ryan and I have found are starting to feel like using a composite geometry and altering the level of theory on a single kind of force field surface is not a good idea. We know that time-consuming additive corrections are expensive but necessary for really accurate results. We haven't tested beyond parentheses Q with the coupled cluster expansion, but we might need to for some particularly tricky problems. And with the magnesium tricarbide system, we've thought about how would we implement a multi-reference CI quartic force field. And of course, we need help and synergy and friendship with all of the brilliant experimentalists that are doing great astrochemistry out there. And with that, I'd like to thank Heather and David for the invitation, Kyle for emceeing, the University of Memphis for funding and startup. Chini Cheng and Atu Agbaglo are the two members of my group that are mostly focused on, or that are that have been able to devote a bunch of their time to astrochemical pursuits. And of course, Ryan and Lucy have been amazing allies and collaborators and friends throughout my entire career. And with that, thank you. Be happy to answer any questions.
All right, thank you, Nate. Very nice talk. We do have a few questions that have come in. I'll take them somewhat in order. These first few are anonymous. First question is, have the computational techniques been used for predicting dipole moments for, say, scandium carbide or the other molecules?
Yeah. Definitely. It can be a little bit tricky to do analytic gradients to get dipole moments with couple cluster theory. So sometimes what, but that just pops out of doing geometry optimizations with multi-reference CI. So I didn't talk about dipole moments, but yeah. Yeah. Definitely the magnesium carbide. All of the isomers have a permanent dipole moment of at least 2.0 dBi. So so their spectra should be poking out of the weeds somewhere. So if folks look for it, but a lot of times, what Ryan and I will do is to calculate NP2 or CCSD dipole moments, because that value can be a little more qualitative. We're just trying to figure out, okay, does it have a large permanent dipole moment or doesn't it? So getting the magnitude of that value perfect is less important than getting really good frequencies and rotational constants.
All right, another a question. It asks, has the computational analysis of, I assume this is valence shell electron pair repulsion theory, been employed on scandium carbide? I think it's because it has a rather interesting geometry. Yeah, I mean, so these are very, if you're thinking in terms of like an inorganic chemist as like a first year chemistry or like a third or fourth year chemistry, in like a third or fourth year chemistry context, right? Yeah, the coordination of these molecules looks totally weird, right? You're certainly not getting to any 18 electron rules of scandium dicarbide, but that's okay because of the how diffuse the molecular material is in the interstellar medium and how cold things are. Is that right? In solution, your scandium would adhere to traditional VSEPR concepts, because if there's no ligands to grab around, it would probably grab water from or acetonitrile if it was in solution to obey terrestrial inorganic chemistry rules. But in space, right, it may have gone, that molecule may have gone 10,000 years without running into another organic molecule. So it can't play by those rules out there. Okay, another question, and maybe the person who asked this can chime in if we need more detail. But the anonymous question asking, what's the threshold energy calculated for the magnesium carbide? I'm not sure what threshold energy is referring to there. So I'll hang on first. I'll move on to another question, but if whoever asked that, if you can follow up and specify what you mean by threshold energy, we'll get back to that question in just a second. In the chat, there's a question from Carl Irakura asking, is there any Fermi resonance in MgC3, like particularly looking at nu3 about equal to 2 times nu6?
Yeah, definitely. Yeah, that's a good question, Carl. Yeah, so we because everything was all messed up with the multi-reference character of that isomer, you know, we weren't able to, like, the VPT2 results were nonsense from the get-go. So trying to like perturb Fermi resonances is just kind of like, okay, well, let's, you know, why bother? But yeah, there's definitely for the triplet diamond, yeah, we did a deperturbation analysis and looked at the resonance shifts, and that's all in the paper. Nothing. Yeah, I don't know. I don't know that the Fermi resonances aren't the cause of the unphysical behavior in the anharmonicity. It's a correlation problem. But yes, we definitely, if there are Fermi resonances or Darling-Dennison resonances that need to be accounted for, we Ryan has taught me well, and we account for those things.
Okay, so the follow-up on the question about the threshold energy for magnesium carbide is referring to the bond energy, like bond dissociation energy.
Oh yeah. So that's calculated, and the yeah, I mean, we just calculated the magnesium C3 bond energy, and that's pretty large. It's 70 kcal per mole for the singlet states.
Okay, and we'll finish up with one last question here. I think this is a more general question about, can you discuss like how the choice of basis set affects the amount of dynamic versus static correlation observed in the isomers that you calculated?
Yeah, that's a good question. So yeah, so it's I think 20 years ago when I was first starting out, it was a lot more challenging to decouple those two things because we couldn't run large basis set CCSD parentheses T in, you know, at the beginning of the 21st century. We couldn't do that very easily. So were some of these strange molecules that exhibited both non-dynamical and dynamical correlation, was that because we were using kind of primitive basis sets, or was it because you know, because couple cluster wasn't appropriate at all? And so yeah, and I think it was with Kirk Peterson coming out with the set of correlation consistent basis sets for the D block, you know, in like 2004, 2005 was a really big deal for inorganic, you know, small molecule transition metal chemistry, because I think what we found out is that the multi-reference behavior is not strongly coupled to the quality of the one electron basis set. And a lot of the work that I did as a postdoc with Angela helped establish that, because nobody had ever tried to answer that question with hundreds of small inorganic, small metal containing molecules before. So certainly, yeah, certainly bigger is better in terms of correlation consistent basis sets. But I think that these composite approaches where you do small basis set post parentheses T calculations and compare those to small basis set parentheses T calculations, those are valid. Those work, with some caveats that Ryan and I have painfully experienced and started to you know, settle in on a more on a good workflow to deal with some of those possible issues.
All right, well, I think we're going to have to wrap things up for today. So thanks again, Nate, and also thanks once again, Jessalyn. This is a great way to get us started for the new academic year with these Astrocheminars. So everyone keep an eye on your email toward the end of this month for more information about our next Astrocheminar, which will be on October 12th. We always try to do these the second Wednesday of the month, and we should be sending out a registration link for you sometime around the end of September, beginning of October. Also, if you would like to submit an abstract to give a contributed talk, please do go to our website. There's a place where you can send in an abstract for us. We'd love to feature more people. It's an especially great opportunity for grad students and postdocs to share some work that you're doing for the community. So please do check out our website for that. We'll get this recording up on YouTube in a few days, and we hope to see you next month or at another one of our future Astrocheminars. So thanks again, everyone, and hope to see you next month.